Today's warm-up question says, Ben needs to move the crate 6 meters to the right. What changes would cause him to do more work? And I think yours is worded like this. I don't remember, or maybe these are your options in your check boxes. But if he pulls it more horizontally, right now he's pulling at an angle of 30 degrees. If he pulls at a smaller angle that's more horizontal, yeah, that's going to cause him to do more work, assuming that the force is the same amount and the displacement's the same amount. He will do more work because more of his force is horizontal. Okay, so pulling more horizontally is going to result in more work if everything else is equal. Carrying the box instead, no. Okay, carrying it isn't work. Lifting it would be, but carrying it would not be. Pulling it faster, well, velocity does not show up in my equation, so no. Velocity is not going to cause him to do more work, changing the speed. Okay, but pulling it a farther distance would, or using more force would. Okay, so that would be your answers to the warm-up. Pulling more horizontally and pulling a farther distance would result in doing more work. Carrying it or changing the speed would not affect your work. All right, so again, please make sure you have answered the warm-up for today in the Google form. If not, go ahead and do that real quick, and then we're going to get into our notes on kinetic energy. Okay, energy is defined as the ability to do work or cause movement, which is kind of a vague definition, but that's how it's defined. Energy is always carried by something, usually in the form of movement, but it can be stored in many different forms. We're going to focus in this unit specifically on kinetic energy. All right, kinetic energy is energy associated with an object's motion. If the object isn't moving, then you have no kinetic energy. You guys should have seen this in the assignment 501 whenever you were calculating the kinetic energy of the marble at the top of the ramp. You had zeros just across those rows, hopefully. You should have, because the marble was at rest initially. Okay, and so you would have zero kinetic energy anytime an object is at rest. You can see that by looking at the equation. The formula for kinetic energy is 1/2 mass times velocity squared. So if your velocity is 0, you will have 0 kinetic energy. In order to use this equation, your masses have to be in kilograms. That has been the case for every equation we've done that has mass. You have to have kilograms. And similarly, your velocity has to be in meters per second. That's the standard units that we use. So if you have a mass in grams, you will need to do a conversion. If you have a velocity in kilometers per hour, you will have to do a conversion. Units for kinetic energy are the same unit we saw for work, that is the joule. We don't really use calories, but it is acceptable as an energy unit. You just have to do a conversion because you want everything in joules. We looked at these factors. This was part of your 501 investigation inquiry activity as well, was the relationships between mass and kinetic energy and velocity and kinetic energy. When you looked at that marble data, there were questions about this exact thing in there. Okay, the relationship between mass and kinetic energy is a directly proportional one. You can see it in the equation. If you were to, for example, double the mass, it would cause your kinetic energy to be doubled. Just look at the formula. If you had 2 times this value for m, you will get 2 times the answer over here. It's directly proportional, so on a graph, it would look like this, a straight line going through the point 0, 0. On the other hand, if you look at the relationship between velocity and kinetic energy, in the equation up here, the velocity term is squared. So this is a squared relationship graphically. That's going to look like a curve like this. And if the velocity were to double, that doesn't just double the KE because that term is squared in the formula. So doubling it would be 2 squared, or 4 times as much. Tripling it would be 3 squared, or 9 times as much. Having 1/2 the velocity would be 1/2 squared, or 1/4 as much energy. So you need to understand the relationships and be able to answer questions like that. If the velocity doubles, then what happens to the kinetic energy? And again, you can copy these 2 examples down. But these are your factors that affect kinetic energy. They're the 2 terms in the equation, mass and velocity. All right, let's try an example calculation. It says calculate the kinetic energy of a 5.2 kilogram object moving at 2.4 meters per second. Again, we're looking for KE. We have a mass and we have a velocity. If you want to label these out like we normally do in the guess method, you can. I just labeled them in the question itself. But here's my equation. Kinetic energy is 1/2 mv squared. If we substitute in, it looks like this: 1/2 times 5.2 times 2.4 squared. Please note, only the velocity gets squared. Please don't square anything else. Okay, so not the mass, just the velocity gets squared. So this is what it looks like when you substitute in: 1/2 times 5.2 times 2.4 squared. Half of 5.2 is 2.6. 2.4 squared is 5.76. Multiply those together, or you could just do it all at one step. And you get 14.98 joules. So the kinetic energy for the object described in this question would be almost 15 joules based on the mass and velocity given. Are there any questions about this particular example? Okay. And let's go ahead and move on. I think these equations are pretty straightforward, and you should hopefully already have them in your notes, because if you took notes during 501, you already have this equation written down. All right, here it says an object has a kinetic energy of 52 joules and a mass of 13 kilograms. How fast is the object moving? Okay, so you could be given the energy and be asked to solve for a velocity or a mass for that matter. But again, if you're given, whatever you're given, just label it, and that way you can figure out how to go about doing this. It's still the same formula, Ke equals 1/2 mv squared, but this time I have the Ke and the mass. So when I substitute, it looks like this, and now I'm going to have to do some algebra. So we're going to have to divide both sides by half of 13, which is 6.5. 52 divided by 6.5 would give me 8, and that would be equal to v squared. Again, I don't want to stop here because that's not the velocity, that is v squared. Take the square root of both sides, and the square root of 8 is about 2.8. And so my answer for the velocity, how fast it's moving, 2.8 meters per second. Questions about this? Again, I hope you guys find this stuff pretty straightforward. It does obviously get more complicated the more equations we add, but we haven't made it too complicated yet. All right, how can the kinetic energy of an object change? Changing mass or changing velocity of an object would cause the kinetic energy to change. Now, we can't easily change the mass of a moving object, but you can change its velocity. How could you cause something to change its velocity? Apply a force to it. Yeah, push it, pull it, some kind of collision, an impulse that applies a force and causes acceleration. Yeah, apply a force for a certain amount of time. Now you've got an impulse, you've got a force, and you have acceleration or change in velocity of that object. All right, so let's look at an example calculation involving something with a changing kinetic energy. This one says a ball with a mass of 2.1 kilograms rolls across the floor of this room. If it has an initial velocity of 6.4 meters per second and experiences an impulse of -5 newton seconds, what is its final velocity? And then find its change in Ke. Again, if I'm looking at impulse, I know impulse was equal to force times time, but it was also equal to mass times change in velocity. I know that from last unit. Because the question doesn't give me a force or a time, I'm going to focus on the stuff it does give me, mass and velocity. So this is the equation I'll use for impulse, which is the change in momentum equation. So I could see that if I were to label everything out, but just looking at it real quick, you can see a velocity, you can see a mass. So this would be the appropriate equation to use. So again, my impulse is -5. My mass is 2.1, and I don't know the change in velocity because I don't know what the final velocity is, but I can use this formula to find it. Again, delta V is VF minus VI. I don't know VF, but I do know VI. So if I plug all of this into my impulse equation, I have -5 equals 2.1 times my delta V, VF minus 6.4, and I'm going to be solving for VF. I'm going to start by dividing both sides by 2.1. If you wanted to, you could have alternatively distributed it into the parentheses, but that's an extra step that we don't have to take, so I won't. -5 divided by 2.1 would be equal to VF minus 6.4, and when I divide that, it's -2.38. So now I have -2.38 equals VF minus 6.4. If I want VF by itself, I need to get the 6.4 out of there. Because it's being subtracted, I need to add 6.4 to both sides. And when I do that, I get this for my final velocity.
Wait, so you get
negative 2.38 plus 6.4 is 4.02 meters per second. That is how you're going to find your final velocity. Okay, so again, copy that down. But you can use any of the equations we've done so far. So you're going to see that in this unit. You're going to see impulse equations. You're going to see momentum equations. You're going to see kinematic equations. You're going to see force, F equals ma. You're going to see all that stuff, along with now kinetic energy equation and the work equation. So we've got a lot of formulas that we can use. We're not done, though. This question also asked us to find the change in kinetic energy. Now that I know how fast it's moving before and after, I can find the initial kinetic energy and the final, and the change will just be the difference. So that's all we have to do for the last part of this problem, is figure out our initial kinetic energy, which is going to be 1/2 mass times initial velocity, which is in the question, 6.4 squared. Okay, and so the initial kinetic energy, 1/2 times 2.1 times 6.4 squared, is 43.01 joules. And then we find the final kinetic energy because we just found the final velocity. The final velocity, again, was 4.02. So we're going to plug into our KE equation 1/2 times our mass, 2.1, times 4.02 squared. And our final kinetic energy is 16.96 joules. And you can ask yourself, does this make sense? And hopefully you think that it does, because the impulse had a negative sign in front of it. So it should be causing it to slow down, which means it should be losing energy. And look at those energies. It goes from 43 to 17. So yeah, it lost energy. That makes sense. If it had gone up, I did something wrong. Okay, so make sure that your stuff makes sense. But now you can find your change in kinetic energy. Change in anything. Change in velocity, change in position, change in kinetic energy, change in momentum. All of those changes, those values for change, can be found as final minus initial. So change in kinetic energy can be found as final kinetic energy minus initial kinetic energy. And yes, this will be a negative change. We clearly lost KE. Okay, so when I go to solve for my change in kinetic energy, 16.96 minus 43.01 will give me a negative number, specifically negative 26.05 joules, and that is your change in kinetic energy. So for this one, we had to use the change in momentum equation to get the final velocity so that we could do this. Okay, and again, that's how we solve this one, but each of them is going to be a little bit different, and all of those equations are fair game. All right, questions about solving change in KE? Okay, at least not for this one. All right, here's another one. A 151-gram toy car is pushed from rest with a force of 0.67 newtons for 1.4 seconds. What is its change in KE? Again, label your givens. Mass, force, time. I have a problem with this. Okay, that mass, I don't want it in grams. You don't either. If you see grams, do a conversion. There are 1,000 grams in a kilogram. Divide this by 1,000 and you get 0.151 kilograms. That's the value that you need. Okay, so now that we have the appropriate units, those all look good. My unknown is, in order for me to find change in KE, I obviously need to know my final velocity so that I can get my change in kinetic energy. So my equation, if I want to find final velocity, because I have mass, force, and time, this would be the equation I would use. F times T equals M times delta V. Okay, and so you can solve for it with the impulse momentum theorem equation from last unit. When I substitute in, it looks like this. Again, anytime you're looking for VF or VI, you can find it with a kinematic equation, if you happen to have that information, or with anything that has delta V in it, assuming you know one of the velocities. And since it started from rest, I do know the initial. Okay, and so this is my substitution step. My force, 0.67, my time, 1.4, my mass, 0.151, and then delta V is VF minus 0 because it started from rest. The left-hand side of my equation ends up being 0.938, and then I have equals 0.151 times VF. Divide both sides by 0.151, and I get a VF of 6.21 meters per second. Now we're not done because the question didn't say what is the final velocity. It said what is the change in kinetic energy. So we need to use this final velocity to figure out the final kinetic energy. My initial kinetic energy, 0, because it says from rest. Okay, so I already know my initial. I just need to find the final. All right, so again, initial kinetic energy is 0, but final kinetic energy, we're going to do 1/2 mv squared using the velocity that we just found, which was 6.21. So 1/2 times 0.151 times 6.21 squared is a final kinetic energy of 2.91 joules. And because my initial kinetic energy was 0, my change is also equal to 2.91 joules, specifically positive 2.91 joules. This toy car has gained kinetic energy because it was pushed from rest. Okay, so it has a positive change. It gained energy. This is an example of a positive delta K. Questions about this? Again, I know we're going fast, so I'm hoping y'all can follow along, and if not, you can go back and look at it. But honestly, the more you do it yourself, the more sense it will make. All right, this one says a 14-kilogram wagon initially moving 3.7 meters per second accelerates at a rate of negative 1.2 meters per second squared as it rolls across rough pavement for 1.4 seconds. What is its change in KE? Again, label everything. We know the mass. We know the initial velocity. This time they gave us an acceleration and a time, and they want us to find change in KE, but that means I need VF. Again, anytime you're finding delta KE, you want VI and VF. All right. I can find VF. I have some options here. Looking at the information I've been given, I have stuff that I can use kinematic equations for. I have VI, I have A, I have T. I can use a kinematic equation because I have 3 of those and I'm looking for a 4th. Alternatively, I see M and A. I could find a force. You could go that route. You have options. Okay, but the fastest route is going to be this one, kinematic equation. VF equals VI plus A times T. Substitute in, it looks like this. VF equals 3.7 plus negative 1.2 times 1.4, which is a final velocity of 2.02 meters per second. Again, once you have that final velocity, you can find your initial and final KE, and you can find the change, and this is your KE equation, 1/2 mv squared. So the initial value was 3.7 in the question, so this would be KE initial, 95.83. My final velocity was 2.02, I just found it, and so my final KE is 28.56. And if you want to find the change, you subtract. Final minus initial. Obviously, it's going to be a negative number because it says it's slowing down. And you can see it in the kinetic energy. It goes from 95 or 96 almost to 28.5. Okay, but you can find the change by subtraction, 28.56 minus 95.83, and that is negative 67.27 joules. Again, I know it's a lot. We're just bringing in old stuff. We're only really adding one new equation today, and that's KE. But because we're utilizing all these older equations, it can feel like quite a bit. And you'll have time to practice it right now. Okay, so as I said, the more you do it on your own, the more comfortable you're going to feel with it. Please make your way to My Open Math and open up the assignment 502.2 Kinetic Energy Problem Set. That is what you should be working on for the rest of the period today. And you guys have about 15 minutes, so you can at least get a handful of those done if you haven't started yet. And then anything that you're not finished with by the end of the period, you will want to finish for homework. If you have any questions, please let me know.